Hello everyone, with this episode I'm going to start sequential games, or sometimes I may refer as extensive form games or just simply extensive games. Don't forget, this is Intermediate Microeconomics 2 course, so we do not lay down all the details of sequential games. Rather, I will just introduce a very simple concept of extensive form game. What we should understand from game tree. So one of the notions that is very important that you should remember at the end of this chapter is game tree. And then the solution concept that we will use for solving extensive or sequential games, which is backward induction. All right, so that's it. So the game tree, what it means, how we should understand or interpret game trees, and then how we apply the backward induction, what it means. All right, so here I'll start with an example. So if you remember, every game must have 4 ingredients. One, the set of players. Here I have 2 players. I call them player A, player B. All right. The second is the actions available to the players. Here, as you see, player A has 2 options, 2 strategies, choices, top, bottom. All right, and player B has 2 choices, 2 alternatives to choose, 2 actions to choose, playing left or playing right. All right. Well, the 3 what the players know at the time they make a choice, and then ingredient 4 was the payoff. So the payoffs are summarized here. So let's talk about the payoffs. Well, let's talk about sort of what the players know at each time they make a choice. So what we call this as game tree, it basically tells us the timeline of the game. And so this game tree tells us the following. The player A begins the game. All right, so the game begins with player A's choice. Well, excuse me, player A has 2 choices. So she's going to choose one of those 2 choices. She will either choose top or bottom. Okay? So let's say she makes a choice, and then according to this game tree, player B will observe player A's choice. If whatever player A chooses, the player B has exactly the same actions, left or right, but obviously her choice is going to sort of affect the payoffs, along with player A's choice, obviously. So if player A chooses top, player will see that. Player B is going to say, oh, you chose top. Okay, well then I will choose either left or right. Okay, so this is different than simultaneous move games, because if you remember, in a simultaneous move game, the idea was players, when they make a choice, they do not observe the opponent's action. Here, however, one of the players, player B here, observes the action of the other player, player A. So player B, if player A chooses bottom, player B again chooses either left or right. And then the game is over. All right, so that's the timeline. So basically, once you see the payoffs, it means the game is over with player B's choice. So because the first player is player A, the first payoff must belong to the first player. This is sort of the convention. And then because the second player is player B, the second payoffs should belong to player B. All right, so whenever you see 1 here, it means for player A. Whenever you see 9 here, it means for player B. All right, so that's the game. Well, the question is, what is the optimal strategy in this game? How do we solve it? Well, by the way, sort of the implicit assumptions that nevertheless I think I should mention at least once. Both player A and B knows the game. All right, so both player A and B basically sees this game tree, just like you and I. All right, so player A knows that if she chooses top, this is the branch the game will move on, and so she should forget about the payoff 2, for example, if she ever chooses top. All right. If she chooses bottom, well, then player B will know that 9 is out of the picture, because the game will not go back to this branch. All right, so that's important. So once player A makes a choice, you cannot undo the action. So that's very important. Both players observe that. Well, can they communicate? Yes, they do communicate. They can talk to each other, etc. But for simplicity, I mean, it may confuse you. It's like, what if there's a communication between the players? So we usually assume that there is no communication between the players, okay? And second of all, third is like, well, as usual, the players are rational in the sense that they are trying to find the optimal strategy to maximize their own payoff, all right? And well, call it as the fourth property or assumption or not, the payoffs that are represented here includes all the psychological, emotional feelings that the players could have towards each other after they observe their actions, all right? So once your opponent chooses an action, and if that action makes you angry, well, it means those payoffs are already incorporating those feelings, all right? So therefore, aside from those payoffs, there's nothing that these agents, there's no secret agenda those players have, all right? So that's sort of the assumption. And once the game is over, the game is over. There's no future, so they cannot, punish each other afterwards, all right? Or they do not play any pre-game. They do not have any other choices. If they had, well, we would have put that choice as a third available action. So if we are putting two actions, that means the player A and B has only two actions, okay? Well, so given that, so think about this game, all right? Pause the video for a moment, if you like, and think to yourself, like, what would you choose? Okay? Well, so here's how we use the concept of backward induction. So the player A knows that her opponent, player B, is a rational person. And if player A chooses top, player B will know that she's at this point and she's going to make a left or right decision, but in either case, she's going to get a payoff of 9. So therefore, player A knows that player B could choose left or right because she's indifferent. All right? So what we do, we put in, well, maybe I should use a different color, right? So player B could choose B or A. Left or right, because both are going to give her exactly the same payoff of 9. So that means if player A happens to choose top, for sure, whatever opponent the player B does, for sure player A is going to get a payoff of 1. Okay. Well, player A also knows that if she chooses bottom, player B will observe that. So she knows that player B knows that the payoffs for her consideration is either 0 or 1. All right. Well, obviously, player B at this point is going to go for the highest possible payoff, which is 1. I mean, 1 is still better than 0. That's also the assumption. I mean, even 0.1 we assume is better than 0. Right? So that means she's actually going to choose right. I mean, a rational agent should not choose left at this point, at this position. So because she is trying to maximize her payoff, she's going to go for 1. So that means if player A chooses bottom, she knows that she will eventually get the payoff of 2. All right? Well, remember, if she knows already, if she chooses top, she's going to get payoff 1. If she chooses bottom, she's going to eventually get the payoff of 2. So basically the choice for player A is whether I should choose something that will bring me payoff 1, or choose something that will eventually bring me payoff 2. Obviously, I'm going to go for the higher payoff. So that means player A should be choosing bottom. All right? And hence get the payoff of 2. So basically, that's the solution. So we say in this game, player A should be choosing bottom and player B should be choosing right. And so you can basically conclude that the outcome is Oops, bottom for player A, and then right for player B. All right, so that's basically the path, the outcome path, with the payoff 2 for player A and 1 for player B. Okay, so that's a backward induction solution of this game. We, of course, have an equilibrium concept for extensive form games, and we call it subgame perfect Nash equilibrium. It's a bit more complicated than backward induction because the concept uses, the subgame perfect Nash equilibrium uses the concept of strategies, and strategies in extensive form games are more complicated animals than the actions left, right, for example. So we don't talk about strategies in extensive form games and subgame perfect Nash equilibrium in extensive form games for intermediate microeconomics course. If you're interested of those materials, you should definitely take the game theory course. But the backward induction solution of this game is bottom right with the payoff 2-1. So that's it. That's the solution. What I would like to do, I like to sort of do a bit more exercise on this case. So think about exactly the same game, same strategic environment, but instead of player A moving first, let's suppose player B moves first. What if, all right, what if player B moves first? That would mean a different game, obviously, right? Because you are changing the ingredients of the strategic environment, like what players know at the moment of making a choice. So here, player B knows the choice of player A, and player A knows nothing because she's the first mover. But once you make that change and make player B the first mover, first player, what you make is like the player B now knows nothing because she's the first player, and then player A knows something because she can observe player B's action. So you change one of the ingredients of the game, and hence that will probably lead to a different set of outcomes. Let's do that. Well, so if player B is, well, all the actions and the outcomes are gonna remain the same. So I keep a big chunk of the strategic environment, except the timing of the players. So if player B moves first, all right, so I put basically the node player B, all right. So she makes a move. Remember, she has two actions, left and right. Okay. Well, once she chooses left, player A will choose. Well, what are the actions available to player A? Top or bottom? Okay, top and bottom. And the game is over, right? What about the payoffs? Okay, so the left and top. So that means player A is playing top and player B is playing left. So it's going to be payoff 1 and 9. But remember the convention. The first player owns the first payoffs, all right? So 9-1. So keep that convention. So the first player, now player B. So therefore I should switch the payoffs, remember. Because the second numbers were belonging to player B. Now it should be the first number because she is the first player. Well, what about the left bottom? Well, player A chooses bottom and player B chooses left. So it's 0-0. Good. Well, if player B chooses right, and then player A observes that choice, and she makes again a choice between top and bottom, all right, and then the game is over. What about the payoffs? Well, player A makes top and player B makes right. So top, right. So 1 payoff for player A and 9 for player B. So therefore, remember, I was switching the payoffs here. So it's going to be 9-1. And, well, this should be the 2-1 thing. Obviously, I should switch it. But just to make sure, it's player A playing bottom and player B playing right. So therefore, that should be the outcome. which is 2 payoff to player B. And so, I'm sorry, 2 payoff of 2 for player A. And so player A is the second player, and hence she's getting payoff of 2 and 1 for player B. Okay, so that would be the game. And then once again, because this is an extensive form game, I cannot use the backward induction in a simultaneous move game because they don't observe each other's actions, but I can use it here. So let's use the backward induction and see what the backward induction solution would be. I mean, it may or may not be different than the other one. I mean, the 2-1. Okay, so player B if knows that if she chooses left, player A is basically going to decide. Remember, player A is the second, owns the second payoffs. So player A is basically deciding whether to go for payoff of 1 or payoff of 0. Obviously, player A will go for payoff of 1. That means she's going to choose the strategy, action, bottom and top. Okay, so I put arrow just to remind me is like where the optimal choice for players will be. All right. So you should definitely do that as well. So that's it. So the bottom, she will never go for bottom, all right? So that's not optimal for her. Well, if player B, however, she knows that if she chooses right, oh, by the way, so therefore player B knows that if she chooses left, she is gonna get payoff of 9. Very good. What about, what if player B chooses right? Well, in that case, she knows that player A is going to consider between top and bottom, right? So if she chooses top, player A, if player A chooses top, she's going to get 1. If she chooses bottom, she's going to get 2. Obviously, player A is going to go for the best outcome for herself. So she's going to go for bottom, all right? And that means player B, if she chooses right, well, she's eventually going to get the payoff of 1. However, if she chooses left, eventually she's going to go for payoff of 9. So that means she should be going for left. Okay? So the backward induction solution of this game, if we change the timing between the players, is going to be left for the player B and top for player A with the payoff to a 9 and 1. All right, so this is for B, this is for A, this is, remember, for A, this is for B. So what happens is that when we change the timing of the sort of the move of the players, like instead of player A, player B moves first, which the outcome changes, which makes a lot of sense, right? Because by choosing left or right, the first player actually has the power to change the direction of the game. So, well, here she cannot really make it. She cannot really change the direction of the game too much because she knows that this 9 payoff for player B, yes, it is awesome, but the thing is, player A has the power to determine whether to go to this branch or this branch, all right? And so moving first gives the players more power, in a sense, more control about their own payoffs, all right? So once again, moving first gives more power to the players about their payoffs, or more control about their payoffs. And so usually the first mover is going to benefit more from being the first mover in comparison to moving in second. All right, so as I said, this is what we call the game tree. And the backward induction, the intuition, I think, is pretty obvious. If you're a rational player, A, here, and if you know you're moving first, you can, what we call, make a rational thought experiment about how your opponent will behave, all right? So you don't observe your opponent's choices, but you can basically expect her to make either left or right decision once the game ever comes to this point. And then you take this into your consideration about what action to choose. All right? So you make an expectation, you make a guess, and it's not an educated guess. You basically know your opponent is rational, and so she's going to go for the best payoff for herself. You take that into account and then choose your actions optimally. All right? So the reason why we call it backward induction is basically, as probably it was clear now through the process that I followed twice in 2 different games, is basically we analyze first the last moving players. All right, so here the last moving player is player B. Here again, player B. And then we move towards the beginning of the game. So we basically sort of a reverse engineering. All right, so we don't start, the game starts from here, and this is the timeline, right? T equals 0, and then game moves in this direction. But the way we solve it in a reverse order. We start from the end of the game, and then we go all the way up to the beginning of the game. And so we call it backward induction. All right? Well, obviously one nice example would be, what if this game was not a sequential game, but a simultaneous move game? What would be different? So let's discuss this as well. So it's going to be just a few minutes of your time, not a big discussion. So I'm going to look at this game. So what if simultaneous? All right. Well, if this game was simultaneous, remember, we always represent simultaneous move games as a matrix game. So because I have 2 players, player A here, player B here, and then the choices, the actions, or the strategies, top, bottom for player A, and then left and right for player B. So, and then fill in the blanks. So top left would be 1, 9. Top right is again 1, 9. Bottom left is 0, 0. And bottom right is 2, 1. Again, the first payoff belongs to the first mover, which is the row player. And the second payoff belongs to the column player, which is the second player. So this transformation is very important. And in this course, basically, that's all we're asking you to understand, the transformation. And then, applying the simple solution concepts. Here, I can't apply the backward induction anymore. The solution concept we discussed is dominant strategy equilibrium, or if it doesn't exist, well, then the Nash equilibrium. So, let's check the dominant strategy equilibrium. The player A has no dominant strategy because top is sometimes better than bottom, but sometimes bottom is better than top. So there is no strategy that's always better for player A. And for player B, right is sometimes the same, sometimes better, but this is not dominance, okay? So this is weak dominance, remember? And so it's not dominance. What we are looking for strictly, so for example, if this was 8 or something less than 9, then I would say, oh, right dominates left, but here it doesn't, okay? So as a result of this, the conclusion, there is no a dominant strategy equilibrium. However, the Nash equilibrium is going to capture this dynamic. You'll see the Nash equilibrium is going to be here. So let's find the Nash equilibrium. So if player A plays top, the regret-free strategy is both right and left because both brings player B payoff 9. If player A happens to play bottom, remember players do not observe each other's actions here. So remember we are calculating the best responses, sort of the regret-free strategies and outcomes. So the bottom, if bottom is the actions of player A, well then right is a better, sort of the regret-free action for player B. And then if player B chooses left, this is the regret-free outcome. If she chooses right, the regret-free outcome is this. So you know what? In this game, there are 2 Nash equilibria, one of which is top left, with a payoff 1 and 9, and then the other one is bottom right right, with the payoff 2 and 1. All right, as you see, we do actually capture this, what happens if the player B moves first business. We actually get that as a Nash equilibrium, which makes sense, right? It's because in the simultaneous move game, you don't observe your opponent's actions. So both of those are regret-free outcomes. So the backward induction and the Nash equilibrium, they're different animals, but they are actually related, okay? And in fact, this is a theorem which we're not going to prove in this course, but the backward induction solution is always, in every game, is a Nash equilibrium solution of the simultaneous move version of this game. All right, so that's something to remember. I hope that was clear.